Good morning, everyone. Happy Monday. Thanks for being here. So I did get around to, I had to grade like one question on your test that was about soap and water. So you should have your grade, your final grade for your test up. If you have any questions on that, let me know. We are working on chapter 6, and we got through the first part of the chapter, which I think is more difficult than the second part. But before we jump into the second part, I want to just refresh that first part with a practice problem because it's amazing how quickly things will just sort of disappear on us, huh? It'll be in there. It'll be in our. Sometimes you know how to do the problem like right before the test, and then you sit down in front of the test and it all disappears. So let's. No, we don't want to go through my email together. Definitely don't want to do that. All right. Different class. So we had this big, hunky, actually, I don't want to erase that. I like that part. We had this big, hunky flow chart that shows us how we can move around compounds and also elements. So just to refresh, right, we've got our compounds. I have it on top. Sometimes you'll see these on the bottom, element on the bottom. And we can easily convert between grams of a compound, moles of a compound, or molecules of a compound, and vice versa. We can do it with elements as well. Gram to mole or mole to gram. This is always our molar mass section. Mole to molecule or mole to atom. That's always our Avogadro's number, right? This is a fixed value. The difference between grams and moles is always unique to whatever the problem is that we're looking at. And then we can actually go in between these two. So I could give you a certain amount of a compound and ask you for an amount of the element, and you can actually flow through because the relationship between moles of a compound and moles of an element are directly related to the subscripts. So let's do a problem just like that. How many atoms of sulfur are in 13.6 grams of aluminum sulfate? So I'll give you about 5 minutes to work on that. Try and get the correct formula for aluminum sulfate. And then if you want, double check yourself with the internet so that you don't run through the whole problem with the wrong formula. And while you're working on it, if there's anything where you're having a real difficulty and you're just sort of stuck, just turn your mute off and ask me for a little bit of help so that we can kind of guide you through it. Just another 30 seconds or so to finish up kind of your train of thought. Okay, so if you've got your flow chart somewhere, you kind of just look at where am I starting and where am I ending. So I'm given information about the mass of a compound. So I've got this thing over here. And I want to get atoms of a specific element. It doesn't say molecules, how many molecules of aluminum sulfate. It's just talking about sulfur. So I need to go all the way over here. So we're kind of going from one end to the other. There's a couple paths you could go from here to here to here and then down. I'm going to cross over in the middle. I'm going to go grams of compound to moles of compound, and then moles of compound to moles of element, and then over to atoms of element. So I'm going to sort of undent that flow chart down here, that everyone's on the same page about what I'm doing. We need to know what aluminum sulfate is as well. So grams of aluminum sulfate, which is Al2SO4 3. So I'm going to go grams of aluminum sulfate into moles of aluminum sulfate. And then for moles of aluminum sulfate, I can go into moles of, what are we talking? Yeah, sulfur. And then for moles of sulfur, I'm going to go into sulfur atoms. And this is why I think that the flowchart is so valuable, because if you notice in this specific problem, are we going into grams of the individual element? No, we're not even going anywhere near that. So that last stage, we're not using the molar mass of sulfur in any of this. If I had asked you instead for like grams of the element, then you would need to use this. But we're not going there. We're actually taking a different path. So we just want to use what the path tells us. So this first step here, we need to use the molar mass of aluminum sulfate. It's a pretty clunky molecule. So I had it written down somewhere. There we go. 300, where were you? 342. So 1 mole of the aluminum sulfate is equal to 342 point, I'll give it 2 decimals, 15 grams. Now, the middle step is where I get to hop from the compound into the individual element, and that's looking at the subscripts. So for every one of these molecules or one of these moles, how many sulfurs will I get? I'll get 3 moles of sulfur, because this 3 gets distributed to the oxygen and it gets distributed to the sulfur. So 1 mole of your Al2SO4 3 yields 3 moles of sulfur. And then the last step right here, this relationship between moles and atoms, anytime you're going between moles and the particles or individual amount of molecules, you use Avogadro's number. So this is 1 mole of anything, in this case sulfur, is equal to 6.022 times 10 to the 23rd sulfur atoms. So that's going to be our process. Then we just kind of set it up in dimensional analysis. Again, as you get more comfortable, you may not need to do this. You may just be able to do it all in the dimensional analysis, and that's fine. That's usually how I end up solving them, but I want to give you the background for now. So we start with our given 13.6 grams of aluminum sulfate, Al2SO4 3. We convert into moles, and we use this relationship. I want to get into moles. So 1 mole of the Al2SO4 3 is equivalent to 342.15 grams of the Al2 ... All right. Next step is to get from moles of the compound into moles of the sulfur. So I'm going to put the compound on the bottom. 1 mole of the Al2SO4 yields 3 moles of sulfur. 3 moles of our sulfur. That will get rid of moles of the compound. And then the last step is I want atoms. So for every 1 mole of sulfur, I will get 6.022 times 10 to the 23rd sulfur atoms. And you just make sure everything's canceling along the way. So grams of compound cancel, moles of compound cancel, moles of element cancel, and we'll be left just with the sulfur atoms. So multiply across the top. So the 13.6, you'll multiply it by 3, and then you've got to multiply it by Avogadro's number, 6.022 EE to the 23rd. And then we divide it by anything that has any meaning in the bottom outside of, we don't need the ones. So 342.15. We're given 3 significant figures. So I'll go with 3 significant figures, 7.18 times 10 to the 22nd sulfur atoms. Does that make logical sense? Yeah, I mean, we would expect to have a lot of sulfur atoms. So, you know, that's how you do it. I say that you need critical thinking, but really, you know, if you've got this chart, it doesn't really require a whole lot of thinking if you've got everything filled in. You just figure out where you're starting, where you're ending, and then follow the path. Okay. Questions on what happened here on this setup, how this setup relates to other problems? Okay, the one thing to note on your flow chart, you cannot go directly between these two. That's why if you remember, I had you put like a red X or something there, because there is no gram to gram direct relationship like that. So keep that out. The next thing that we're going to do is looking at mass percents. You will not use this. Okay, so if you start to see problems with mass percent, empirical formula, things like that, we won't want to reference this. Okay, so here's the equation for mass percent or mass percent composition. Like if I was to say, hey, how much aluminum is in aluminum sulfate, like mass percent wise, what percentage of the mass is coming from aluminum? Well, you take the mass of X just being whatever element it is that you have picked for that problem. You divide it by the mass of the entire compound and you multiply it by 100. I mean, that's what a percentage is. It's the part divided by the total times 100. So let's do that for aluminum sulfate, okay? Since we already know the formula for it. We've got Al2SO4 3. If I want to figure out the mass percent of aluminum, so what's the mass percent of the aluminum? I need to take the mass of the total aluminum in the sample. Now, if you notice here, do we have more than one aluminum? We do, so we need to take that into account. So the mass of aluminum is 26.98, but I have 2 of them. All right, so I do need to multiply it by 2. If I had 3, I'd multiply it by 3 because that means you have more aluminum. Yeah, Carrie?
We can't see your writing. I can't see your writing. It's
you know what? I think
it hasn't been cleared out on my end.
Okay, hold on one second. Let me re-share. Let us try now. Are you with me now on the slides? No?
It's your screen with the compound and element
It's
pathways.
still with the flow chart? So nothing now, right? Your screen.
No.
I'm trying to. So you, anything PowerPoint? Why it's, yeah, you can see it now.
Yep.
Elizabeth.
Got the
Okay.
PowerPoint, yes.
Okay, perfect. Great. Yeah, that'll make more sense if you can see what I'm talking about. So mass percent. So mass percent composition, you take whatever element it is you're looking at. So mass percent of X is going to equal the mass of X in the sample of the compound. And that includes, like, if you have 2 of them or 3 of them, you've got to multiply it by however many you have, divided by the mass of the whole compound times 100. So again, percentage is always the part divided by the whole times 100. So again, yeah, let me write out what I was saying. I'm gonna do it over here anyway. So if we have aluminum sulfate, SO4, and we want to find mass percent of aluminum, okay, that's going to equal the aluminum, so 26.98, but we've got to multiply it by 2 because there's 2 of them, so they carry more weight in the total. We divide this by the total molar mass of the molecule or the compound, and that we had, what was 342? Something like that, 342.1 something. I don't remember exact, it's close enough, 1.5. Yeah. And then we take that whole thing and we multiply it by 100 to get it into a percentage. So the 26.98 times 2, and we divide it by 342.15, and then we multiply it by 100. And so what we end up getting is that roughly 15.8% is aluminum, or 15.8% of the mass is aluminum. Let's do the mass percent for sulfur. So the mass percent for sulfur, well, sulfur has a different molar mass, right? It is 32 or 32.07. How many sulfurs do I have within each molecule here? I've got 3. So I'm going to multiply it by 3, and then I'm going to still divide it by the same total, right? Because we're talking about the same compound, so 342.15, and then we multiply it by 100 because that gets us into a percentage value. And for this one, a little bit more, 28.1%. Okay. I want you to do the last one. I want you to find the mass percent for oxygen. All right, so the molar mass of oxygen is 16, but again, we need to determine how many oxygens are actually in there. So there's a total of 12 oxygens. 4 times the 3. Right, we multiply our subscripts for a total of 12, and we still divide it by the same thing, 342.15 times 100. So the majority of it is actually oxygen. I get 56.1%. Now, ideally, when I add these 3 together, what should my total be? It should be 100%, right? Because there's no other things that we have to take into account. So 56 plus the 28.1 plus the 15.8, and I get 100%. Okay, so that's one way to check Some people will kind of deduce that, oh, if I've already figured out aluminum and I've figured out sulfur, I should really easily be able to figure out the oxygen. I could just subtract these from the 100. You could do that as well. I want you to tell me the mass percent for, we've got HCl, hydrochloric acid. Do the mass percent for hydrogen. And, you know, while you're at it, do the mass percent for chlorine. Okay, so hydrochloric acid, first thing you really kind of want to do is figure out the total for this thing. So the total molar mass for this is 36.458 or 36.46, that'd be fine. It's a hydrogen and a chlorine. So what is the mass percent of hydrogen? Sometimes people will look at this and they'll say, oh, well, the mass percent isn't it 50% for each one? No, because the chlorine atom is much, much bigger than the hydrogen atom. So when finding mass percent here, we need to take the part divided by the total times 100. So the part's mass, the hydrogen's mass, is really small, right? It's just 1.01 or 1.007. Divided by the total, which was this 36.458, and we're going to multiply it by 100. 1.01. I got roughly 2.77%. So a small percentage of it is hydrogen. Even though it's a whole hydrogen atom and a whole chlorine atom, it's a 1-to-1 ratio. The mass of the hydrogen is much smaller. Chlorine, you could do it two different ways. You could take 100 minus this to get roughly the value, or I'm going to just do it the traditional way. So 35.45 is the mass on our chlorine divided by the 36.458 and times 100. And we get something like 97.2%. So if I was to add these up, wouldn't be exactly 100, but it's pretty close. Yeah. Does that feel easy?
I have a question.
Yeah, what's up, Carrie?
I rounded 30 to 36.5. Should I not do that, or is that okay?
I think you'll be okay if you rounded it to 36.5. Yeah. You're not,
Okay.
this isn't going to be something where like one of the answers is 2.77 and the other one is 2.79%, right? We're not going to have options that are that close to each other. So as long
Okay.
as you're keeping a decimal or two, you should be good to go. What I don't want you to do though is round to like 37. Okay, because then you are starting to lose some mass and that can have an effect. Other questions on this? I mean, it's not that complicated, right? This kind of feels easy after what we did for the first part. So if I give you a formula, you can figure out the mass percents, right? Well, what if I give you the mass percents? Could you go in reverse and come up with a formula? Yes, you can. This way is a little bit more complicated though. Okay, this way is kind of easy. This way has a couple extra steps, but I'll teach you guys the steps. Not really into this, kind of skip over that. Okay, so if you have the chemical formula, how do you find the mass percent? You take the mass of the individual divided by the total times 100. If we have the mass percent of each thing or the mass percent composition, can we go back to the chemical formula? And we can. In order to talk about that though, we need to review a couple things. One thing is the relationship between an empirical formula and a molecular formula. So remember, an empirical formula is a formula with the smallest whole number ratio of each atom. A molecular formula is a formula that is got the same ratio as the empirical formula, but it's multiplied by some value. So hydrogen peroxide is a great example. The hydrogen peroxide, what's actually happening in real space is two hydrogens are bonded to two oxygens. So it's H2O2. That would be the molecular formula. It's a multiplier. The empirical formula, on the other hand, would just be HO. What is the most basic ratio between that molecule? It's that there's a hydrogen for every oxygen. So how we relate the empirical formula to the molecular formula is this value known as N. And N is just a number that we use to multiply. So the N value for hydrogen peroxide is 2. The empirical formula being HO, the molecular formula being H2O2. How do I get from this to this? I have to multiply it by 2. That's it. So let's do, I want you to tell me what the N value is for this. I'm just going to give you the molecular formula. I'm not going to give you the empirical formula. Whoa, what happened there? So here's a hypothetical molecular formula. H11O22. Sorry, let me put a C in front. C44H11O22. That's the molecular formula. I want you to tell me what is the empirical formula and what is the N value? Okay, so in order to write an empirical formula, I just want to look at what the molecular formula is and see what is everything divisible by. Now, if it isn't divisible by anything, if you can't divide across and still have whole numbers, your molecular formula is your empirical formula. They're the same. But in this case, I can actually divide everything here, right? I can divide all of them by 11. So that actually becomes your N value. It's equal to 11. Empirical formula then would be C4, H1, so just H, and then O2. You could write a little equation that says, hey, if I take C4H02 and I multiply it by my N value, N, and then N is actually 11, I will get my empirical formula, which is C44H11O22. How do these relate to each other? Well, N has to be 11. It's whatever you're dividing it by. So if you were to be given something like this, for LiPO4, if I said, hey, this is your molecular, what's the empirical? Well, can I divide those by anything? No, so the empirical formula would also be LiPO4. That happens sometimes. Sometimes you get molecular and empirical being the same. A lot of times it happens with salts. And then what would my N value be for this one? It would just be 1, right? An N value of 1 states that molecular is equal to empirical. So it's important to be able to differentiate between molecular and empirical because we will be doing some calculations with that. Let's go back over here to the slides. So if you're given some experimental data, like say we're decomposing water, and we started off with a certain amount of water, and when I decompose it, I get 24 grams of oxygen and I get 3 grams of hydrogen. And I want to determine its empirical formula. Well, you know what the empirical formula for water is, right? H2O, but we're going to prove that. If I have the values for the individual amounts, I can go through this process to work back to an empirical formula. And these are the steps. So first, write down or calculate as given the masses of each element. If for whatever reason you are given percentages, like instead of saying 24 grams, I said 24%, just assume it's a 100-gram sample and we can get rid of gram and just put it as percentage. Okay? So let's do that. First step is to write down each of them. So for the problem that we were looking at, we had 24 grams of oxygen, right? And then we also had, don't even remember, what did it say? 3 grams? Yeah, 3 grams of hydrogen. So you're given the amount of each, and we want to come up with an empirical formula. So first write those down. Again, if it's a percentage, just assume a 100-gram sample and take the percent value, rip it off, write it as a gram. Next step is to convert each mass that you've written down from step 1 to moles using the appropriate molar mass. So formulas are not mass relationships, right? They're molar relationships. When I say H2O, I'm not saying 2 grams of hydrogen for every 1 gram of oxygen. I'm saying 2 moles of hydrogen for every 1 mole of oxygen. So I need to get out of grams and get into moles. So in order to get out of grams of oxygen, I need to use the molar mass. 16 grams of oxygen will yield 1 mole of oxygen. I use the oxygens with the oxygens, and then we'll use the hydrogen molar mass over here. 1.01 gram of hydrogen will yield 1 mole of hydrogen. So that's the next step, is to get from grams into moles. And in this case, 24 divided by 16 gives us what, 2? I can't even think today. 1.5 moles of oxygen. And then over here, I've got my 3 grams and then I divide it by 1.01. And I get 2.97. This is where you're gonna do some rounding, okay? So 2.97 moles of hydrogen. It's roughly 3. So they have it down here as 3. Yeah, so they converted to 3 grams. So the next thing that you're going to do once you've converted into your moles is write down a pseudo formula for the compounds using the moles as each subscript. Because this ratio, I'm just going to change this to 3 because it's close enough to 3. This ratio is correct. It's 3 moles of hydrogen for every 1 mole of oxygen. So hydrogen gets a 3, oxygen gets a 1.5. That's our pseudo formula. Now, why don't we like this? What is wrong? Not wrong, but like what isn't working here for us? It's the fact that we have a decimal, right? We don't like to have half atoms. So we have the correct ratio. We just haven't gotten it to a whole number. So the quickest way to get this to a whole number ratio is the next step, which is divide the subscripts in the formula by the smallest subscript. So whatever the subscript is that's tiniest as far as a decimal is concerned, divide it by that. And you don't just divide this one, you divide the whole thing. So the smallest subscript here is the 1.5. So I'm going to divide everything by 1.5. What is 3 divided by 1.5? It becomes 2. What is 1.5 divided by 1.5? It becomes 1. H2O. Look at that. We were able to come up with the formula for water from experimental data. Where is this experimental data going to come from? That will always be given to you, okay? If we were in a lab setting, you would like get it experimentally, you know, but we're not running any labs. So this stuff, this initial stuff here, this and this will be given to you. You'll be required to go through the rest of it. So this is like step 1, write it down as grams. Step 2, convert it to moles. Step 3, turn it into a pseudo formula. Step 4, divide by the lowest subscript, and then hopefully step 5, you get the formula. What if after you divide by the lowest number, you still have a decimal? And that does happen. In that case, you will, if the subscripts are not whole numbers after you divide by the smallest one, multiply the subscripts by some sort of whole number on the following table. That will get you to a whole number. So let's look at this here. So let's say after you divided, you still had like a 0.5 lying around. You would multiply everything by 2 to get rid of that 0.5. We don't want to round those. The only time you round is when you are within like a tenth. So if it was 2.93, you could round that to 3. If it was 2.5, you would need to use a multiplier. So let's try one of these. Where do I want to go? All right. So let's look at this one, this first one here. An oxide of chromium, and when they say oxide of chromium, they just mean chromium with oxygen, is found to have the following percentages. It's 68.4% chromium, and the remaining 31.6% is oxygen. Determine the compound's empirical formula. So this one has a little bit of an extra step. If you see percentage, just assume it's a 100-gram sample and you can change that to gram. So just take your percentages right off the bat and turn them into gram. I want you to go through the process of converting from grams to moles, write a formula, divide it by the smallest, and try and get yourself to whole numbers. I'm gonna give you 2 minutes to, or maybe 3 minutes to go through that. Same process from the last one with the water. Okay, so following this system, and again, I think sometimes the hardest thing is just knowing when you're looking at a problem, what am I trying to do? So if it's giving you mass percents and it wants empirical formula, this is the system you're going to follow. Whenever you see percentage with one of these, you can assume 100-gram sample. I'm just going to erase those and replace them with a gram. Okay? So that gets us to the gram step. Now, we don't want to stay in grams. We need to get it into moles. I see regularly students just going with these values and dividing it by the smallest one. No, first we got to get a molar relationship. So 1 mole of chromium is going to equal our 51.996, something like that, grams. For oxygen, 1 mole of oxygen is always 16 grams of oxygen. So we calculate those out so that we can get our mole values. So for the first one, I got like 1.32 moles of chromium. For the second one, I got 1.975 moles of oxygen. So now we write a pseudo formula. Some people just divide here instead of like writing out the formula. You can do that as well if you want to. I'm going to just write it out. Chromium 1.32, oxygen 1.97. I mean, that's close enough to 2, but I'm just going to keep it intact for now. So this is a correct ratio. It's just not a whole number ratio. So let's divide by the smaller of the two. That's this one, the 1.32, and hope we get a whole number. So chromium, that 1.32 divided by 1.32 will be a 1. And then the 1.97 divided by 1.32 gives us oxygen 1.5. You guys get that? Chromium went to a 1 and the oxygen went to a 1.5. Yay, nay, maybe. So yeah, okay. So now we still have a decimal, right? It's still not a whole, it's getting closer to being like cleaner, but it's not quite there. So the last thing we need to do is we've got to multiply by some sort of number to get it to whole numbers. If you have one as a 0.5, we will multiply it by 2. It's kind of like, you know, a half, you need 2 of them to get to a whole. A quarter, you need 4 of them to get to a whole. A third, you need 3 of them to get to a whole. If that isn't ringing a bell for you, you can just use this, okay? So if one of them still has a 0.5 left over, multiply it by 2. And you have to multiply everything by 2. So I'm gonna multiply all my subscripts here by a factor of 2. What does that do to chromium? Chromium now becomes 2. What does oxygen become? Oxygen will become 3. So Cr2O3. So grams to moles, divide by the smallest, hope you get whole numbers. If you don't, multiply it by some sort of factor to get you to whole numbers. Y'all want to do one more of these? Yeah, why not? Okay. So let's say that and there's a bunch of practice worksheets, like that one that I pulled up. There's another one as well that you can do. I'm going to give you a different one. So let's say that you have, what is the empirical formula for 57.14 grams of carbon, 6.16 grams of hydrogen, it's a 6.16 grams of hydrogen, 9.52 grams of nitrogen, and 27.18 grams of oxygen. Okay, so you have 4 different things here you get to calculate. So I'll go ahead and give you 4 or 5 minutes for that one. Okay, so for this one, you get to do 4 elements. Probably wouldn't see anything with more than 4 elements. So we've got 57.14 grams of carbon. It's not in percentage, so we don't have to switch it to grams. It's already there. I know I'll right off the bat, I've got to convert it into moles. So 1 mole of carbon is 12.01 grams of carbon. Next one here, hydrogen, 6.16 grams of hydrogen. We'll convert 1 mole of hydrogen is 1.01 grams of hydrogen. Nitrogen, 9.52 grams of nitrogen. 1 mole of nitrogen is, got the molar mass 14 grams of nitrogen. And then the last one, we've got our oxygen, 27.18 grams of oxygen. For every 1 mole of oxygen, we get 16 grams of oxygen. So solving for all these, I get 4.76 moles of carbon, 6.10 moles of oxygen, 0.68 moles of nitrogen, and 1.70 moles. Wait, why am I saying oxygen up here? It's hydrogen. If you're wondering when you're given these, like what order should you put the formulas in, just write them. I know like for this is organic stuff, so you don't kind of know the setup for it. But if it gives you carbon first and then hydrogen, nitrogen, oxygen, just write them in that order. Okay, write carbon first, then hydrogen, then nitrogen, then oxygen. So once we've gotten to this stage, we need to divide all of these by the smallest number. And in that case, this is the smallest number. You could write the pseudo formula, or you can just divide here. 0.68, 0.68, 0.68, and 0.68. Let's keep our fingers crossed and hope that we get whole numbers. All right, well, the first one is close enough to be 7. We're gonna go with 7 on that one. This one will be, it's like 8.97. 97. We can say that's 9. That's close enough to be 9. This will be 1. And then the last one here is roughly 2.5. So are we at whole numbers? Almost. What's holding us back here? Our ratio is good, except for this thing right here. So I have to go through and then multiply everything by what factor? Well, what's left is 0.5. So 2. Multiply this by 2, by 2, by 2, by 2. So you should get 14, 18, 2, and 5. Write it in the formula. So carbon will have a subscript of 14. Hydrogen will have a subscript of 18. Nitrogen will have a subscript of 2, and oxygen will have a subscript of 5. Some of these organics can get pretty clunky and cumbersome, so don't get freaked out if you see big numbers like that, okay? So that is how you solve an empirical formula from experimental data. You can go either way now, right? You can go from chemical formula to mass percentages, or mass percentages or experimental data to empirical formula. This way is much easier, I think, than this way. This way requires a couple extra steps. Now there's a little bit more to this, because everything we've been solving thus far has been empirical formulas, but we know that there are molecular formulas out there. So there's an additional little thing that I will get into, but I'm going to leave it for Wednesday. I don't want to get it started right now. So we are done for today. If you have any questions on any of that stuff, hang around. If you've got any individual questions, feel free to ask. Otherwise, enjoy the rest of your day, and I will see you all on Wednesday. Bye, guys.